Let's talk about states of matter. When we say states of matter, we think solid, liquid, and gas. But there's actually some states of matter for the super hot and the super cold. Super hot is called plasma, so this is a superheated gas. And on the other side of the spectrum, the super cold, it's called a Bose-Einstein condensate. Kind of a physics term, but it's interesting to talk about. Kinetic molecular theory, if you recall, says that matter is made up of particles which are in constant random motion, and they collide with each other with perfect elastic collisions. And it's a way to describe gas particles, but we can also apply it to solids and liquids. First of all, let's talk about solids, this state of matter. So when we look at a solid, it seems like everything's still. I mean, it's a solid. But at the molecular level, we have the atoms or the molecules vibrating about in a fixed position. We describe the shape as being definite, meaning that it has its own shape and it has a definite volume that we can measure. So when we look at the volume, two ways to calculate the volume. If we have kind of a cubic solid, we can do length times width times height to find that volume. If you have an irregular solid, recall that we can use water displacement. So first of all, measure out the height of your water, then put your solid in, and then notice what the height is now. And the difference there, this is your volume. When you look at a solid vibrating around a fixed position, so the molecule is just vibrating in place and its neighbor is also vibrating in place. So you might have the atoms a little bit closer to each other, a little bit further away, but when you look at the regular structure of a solid, you can see that there's a point that all these vibrations are around. And so that point would make up that crystal lattice. So you can see that regular pattern of the solid. Let's go and add some heat to our solid. So now the molecules are going to be vibrating faster and they're going to be colliding with their neighbors even more. And that kinetic energy will help them to break free of those intermolecular forces, at least just a little bit. They're still there, but now the molecules or the atoms are slipping and sliding past each other, and we have what's called a liquid. So in a liquid, we describe its motion as it's vibrating around a moving point. So if you have a beaker full of water and you're looking at one molecule, you'll see that it's vibrating, but it's colliding with its neighbor, and it's traveling throughout the sample there. So again, it's described as vibrating around a moving point because it seems like there's a point that's moving around, but then it's also vibrating. As far as its shape, it has an indefinite shape and a definite volume. So we can just measure the volume by putting the liquid into a graduated cylinder, and then the indefinite shape, it will take whatever the shape of its container that it is in. Let's add some heat. So the molecules are slipping and sliding past each other, and they start going faster and faster, and pretty soon the collisions become a little bit more violent, and the molecules start to be able to break free completely from their intermolecular forces, and we have a gas. In a gas, the collisions are elastic, as we mentioned before. The particles are far apart from each other, and when they do collide, when they do travel, they travel in a straight line, and then they'll collide with their container or with other particles, and then they'll bounce off. As far as the shape, they have an indefinite shape, meaning they take the shape of whatever container you put them in, and they'll also expand or contract to fill whatever volume that you put them in. Let's add some heat. And so now the collisions in the gas, they are becoming even more violent, and so colliding with each other, and we make another state of matter that is associated with really high temperatures. And the question is, will everything be just a gas? And it will not just be a gas. Instead, the collisions are so violent, those electrons are knocked off the atom, and so we have ions, positive ions and electrons zipping around. They will be able to be controlled by a magnetic field because it is what's called an ionized gas or a plasma. Just like a gas, it will have an indefinite shape and an indefinite volume. And this is the most common state of matter throughout the universe. So when we look throughout the universe, we see solid planets that are frozen, but we also see a lot of stars out there. And stars are made up of plasma. Some other places where plasmas are found: flames, hopefully didn't scare you there, lightning, and also, as I mentioned before, stars like our sun. Here's another diagram that shows some other types of plasmas. So there's the northern lights, the aurora borealis. We have neon signs. So the lower temperatures are associated with an electrical current going through the material, which is ionizing the gas. But it is described as being a plasma. So your states of matter: solids, liquids, and gases. We are adding energy as we go from phase to phase. The particles are moving faster and faster as we go from phase to phase. All right, let's go ahead and talk about the supercold. So a Bose-Einstein condensate, it was predicted in the 1920s by a professor from the country of India, and he wrote a letter to Einstein proposing his ideas, and Einstein wrote back and thought that Bose's ideas were really good, and they actually collaborated on this. It wasn't until 1995 that they're able to prove this, that the ideas that Bose and Einstein had were correct. So what happens is, as it gets really, really, really cold, the Heisenberg uncertainty principle applies. So we go back to the quantum ideas with quantum mechanics. So we do know the momentum. The momentum is, it's still, nothing's moving. And so because Heisenberg said the more you know about the momentum, the less you know about the location. That's what's going on with a Bose-Einstein condensate. So the atom kind of doesn't know where it is. So it's really, really at rest. It's still, and the atoms start to clump together, and they start taking on all the same qualities. And I describe it as kind of a big blob, like a super atom, and it's just at rest. There's a picture here that shows a Bose-Einstein condensate. Really, I don't know what it's showing, but I think it's kind of interesting that at the super cold that the atoms act differently. All right, so here's a diagram for the states of matter. You can stop this and answer your homework question. And you need to know the different properties of solids, liquids, and gases, and plasma, and what's going on with each of them.